Okay, so let's say you're given this problem to derive the formula for the volume of a sphere. Uh, well, okay, let's say that, you know, you are, inside of a little room and you're trying to figure out how back in the day these great mathematicians figured out how do you come up with a formula for the volume of a sphere? Well, you might have memorized it and you think you know, but you don't really know. So let's take a look. We have a sphere. And now this sphere, well, it's a little oddly shaped, but it'll do pretty well. Okay, so you stare at this little sphere for a little while. You notice it's pink. That's okay. And you're trying to find the volume. Well, maybe you can find the radius of this sphere with a ruler. Well, that'll help. Let me grab a ruler here. Okay, so I found a ruler. You can measure the radius. The radius, well, that's about almost 1 inch, give or take. Well, it doesn't really help you much. Maybe we can come up with a way to, well, you might be thinking, well, you can mush it up into a square because it's Play-Doh. But that's not really the point, right? The point is to figure out the formula for the volume of a sphere. Not just this sphere, but any sphere. Any sphere. Well, this sphere, we know it has a radius. And, well, that's pretty much all we have, right? Well, you stare at it for a while. We can wrap a little ruler around the entire thing. You can mush it up with your fingers. But you might be thinking, well, what if we break it down into smaller chunks? What if I cut this guy in half right here? Wow. Okay. So this is half of a sphere. Now, obviously, I squished this up a little bit, but so here I have a little sphere, half. Now what if I sliced it up again? That didn't work out too well, did it? But that's okay. Take a look at this. So if I take a slice out of this sphere, I have what's the shape of this guy? Or well, it's supposed to be a circle, of course, but obviously I'm not very good at cutting. Well, let's take a look here. I mean, this circle, let me try to draw an outline of this circle. This circle, well, this circle has a radius. Well, that's a slice, and well, notice that you can find the volume of this this slice. The volume of a slice. So the volume of a slice. Volume of the slice is equal to the area of the slice times the thickness of the slice, right? This thickness right here. Okay, well, we know that. Well, why don't I just cut it up into a bunch of slices? So if I cut this little sphere, if I cut another slice, well, I would have another circle. Let's say I do the same thickness. This guy, even though I squished it up, because my knife isn't very sharp, but that's okay. We want it to be safe, right? We need safety. Now here, this guy will, oh, hold on, this slice right here. So this slice, notice this slice, well, this slice, the big one, came from the exact center of the circle. So this one that's smaller, I mean this one's, it's a smaller slice. This one came from, you know, outside of the circle. Well, I mean this, think of the Riemann sums. This is a big idea. So if you think back to the Riemann sums idea, this is why the Riemann sums are so important. Is that, remember when you were trying to find, so let's forget about the circle for a second. You had a curve, you're trying to find the area underneath the curve. The idea was that you took some rectangles. Let's do a left hand approximation. Let's say you're, you know, and so the area underneath the curve is equal to the sum of 0 to n minus 1. So this is the left area approximation. So the sum, this is given by f of x sub I times delta x. Right? You guys remember this? So this gives you the, remember this is the area of each rectangle. And then to get to the actual area underneath the curve, remember what you did is you took the limit, you basically made these guys infinitely small. So you took the limit as n goes to infinity of this guy, basically. And so, well, if you think about it, so this is, you're taking smaller and smaller rectangles, infinitely small rectangles, to find the area underneath the curve. The exactly same idea applies here, is that you know that you can find a slice of a sphere. So this is my slice of a sphere. If you just keep slicing it up, let me put a couple more slices here. So you take a slice, and then you take another slice, and then you take another slice. Well, this, you know, this is going to approximate the volume of the sphere. So each one of these, you know, this is an approximation. So let's write this down. So the volume, let's try to figure this out. So the volume is approximately equal to the sum from 1 to n of the area of the slices times the thickness. Right? Because the volume of each slice is equal to the area times the thickness. Now this is just the idea of it. So let's try to formalize this idea. I have a new piece of paper here to try to figure out what's going on. Try to come up with a way to volume. Now, take a look at this. So this is my sphere, and so my sphere has. So let me draw the sphere here. So this sphere looks something like. Now I'm a terrible drawer, obviously. You guys already know that, but I'm gonna give it my best. Okay, so this is supposed to be a sphere. It's supposed to be this sphere. This pink sphere. That's not that bad. Okay, now, this sphere, so remember the idea is that we're going to take slices. We're going to take slices, and we're going to, so let's say, for example, this is a sample slice. This is going to be a sample slice here. Now, these sample slices have a certain radius. And so if you take a look at this and you imagine the whole idea behind the Riemann sum, this is pretty much exactly the same, is that you're going to take a slice that is infinitely thin in width. So these slices, what you're going to do with them is you're going to add them up. And so the expression that symbolizes that is the integral. So if you take a look at this, so this is going to be, so this is, let's call this is the radius of the sphere. Let's call this r. So this is going to be r. So negative r and r. And then the radius of these small spheres, the little slice, that's going to be small r. Okay, so what we want to do is we're going to take the, so the volume is basically the integral from minus r to r of the area with respect to x dx. Now, well, remember what this means is that what this basically means is that we're going to take these guys, the area of small slices, and what we're going to do with them, so here's our sphere again. What we're doing is we're taking slice and slice and slice and slice, and what we're doing with these slices, so this is this, we've got a slice, this is a slice, this is this little slice right here, here we've got another slice, right here. Now what the integral does, remember, is it makes the slices infinitely thin. So like if you imagine these guys, these are the slices that make up the sphere. Well, the integral makes these slices, I mean these would just approximate the sphere, the volume of the sphere, but if you make these slices infinitely small and you go from negative r to positive r, what you're basically doing is you're sweeping through, catching the volume of the sphere. And so the volume of each slice is the integral from negative r to r of the area. Now we haven't found the area yet. The area of a sphere, the area of each little slice, each one of these green slices is equal to pi times the radius squared. Now the problem is that, well, you need to make it with respect to r because that's what you're integrating with respect to. Okay, so what it is you assume here that you know what x is. So this is x. And if you're trying to figure out what r is, well, if that's x, then, and you know that this right here, this length is going to be equal to r, that's the radius of the big sphere, then this guy, the radius of this green guy is the square root of r squared minus x squared. And r is a constant, of course. Okay, so the area of each little green slice is going to be pi r squared, but r is this guy, square root of capital R squared minus x squared. So this is going to be pi times r squared minus x squared. Okay, so this guy, so this is what I'm going to get the integral of. So this is going to be the integral from minus r to r. What I'm going to do, I'm going to take pi outside because it's a constant. And so pi and then r squared minus x squared dx. And this is the integral that I'm going to find the volume. So here this is equal to pi times, r is just a constant, remember, so this is going to be r squared x minus x cubed over 3, that's the antiderivative of that guy, and then I'm going to evaluate it from negative r to r. Okay, so this is all kind of coming together now. So here what I have is pi times, so if I plug in r now, I'm going to get r cubed minus r cubed over 3 minus, let me put another parentheses here, so it's going to be minus, if I plug in negative r here, I'm going to get negative r cubed, and then I plug in negative here with this negative is going to be plus r cubed over 3. And this, well, this negative and negative turn to positive. So really what I have is going to be pi times 2 r cubed minus 2/3 r cubed. And this is equal to 4/3 pi r cubed, which is the volume of a sphere. Isn't that neat?